Hello, everyone. My name is Guolei Zhong from Center for Complex Geometry Institute for Basic Science. Um, Joined with my collaborator, Professor Fei Hu from Nanjing University, we wrote a paper titled Canonical Heights for Abelian Group Actions of Maximal Dynamical Rank, which got published in Forum of Mathematics Sigma recently. Today, the aim of this video is to give a brief introduction to the topic of our paper, and we hope that this can attract the readers' more interests in our research topic. I will briefly review the important notions in our paper, and after that, I will introduce the main result. So we start from a smooth projective variety of dimension n. Here, in this project, we mostly work over the field of algebraic numbers. And we denote by auto X the group of all holomorphic automorphisms of X. And then for each integer p between 0 to dimension n, we define the piece dynamical degree of each element g to be the limit of the iteration g power k pull back this self-intersection hp for p times this hn minus p. And then we take the kth root, okay, and let this k to be infinity. And here this h is an ample divisor. So by the work of Ding and Sibony in 2004, this limit exists and always independent of the choice of the ample divisor h. So this piece dynamical degree is one of the most significant invariants in dynamical system. According to Gromov-Yomdin theorem, the maximum of the logarithm of all dynamical degrees equals the topological entropy. We use h top g to denote. So roughly speaking, the topological entropy measures the divergence of orbits. And an element G is of positive entropy if the topological entropy is positive, or equivalently, the first dynamical degree is greater than 1. Indeed, by the log concavity of the dynamical degrees, this is also equivalent to all the dynamical degrees greater than 1 if this P is greater than or equal to 1. Okay, so clearly this D0 G is always equal to 1. But for the positive entropy definition, we require all of the dPg is greater than 1 for whenever this P is no less than 1. A group G is of positive entropy if every non-trivial element in G is of positive entropy. So this is our key object in this paper. So Ding and Sibony studied the structure for an abelian subgroup of automorphism, group X. So if G is an abelian subgroup where X is a compact Kähler manifold of dimension n greater than or equal to 2, then we can decompose G to the product of U and H, where this U is the zero entropy part. This means the topological entropy vanishes, or equivalently, all of the dynamical degrees equal to 1. And this H is the positive entropy part. And this H is a free abelian subgroup with the rank no more than n-1. So usually we call this rank of this H, the positive entropy part, to be the dynamical rank. So this means the dynamical rank should not exceed n-1. And moreover, if the rank of this H achieves the maximum dimension -1, then the zero entropy part is actually a finite group. Okay. So for each automorphism group, auto X, so the identity component for this auto zero, we know this is the continuous part of this auto X. And every element lying this connected component of the identity is of zero entropy. So we can imagine that this discrete part H, which is of positive entropy. So this structural theorem describes the discrete part of this automorphism group. Okay. And furthermore, Ding and Sibony showed that indeed these rank estimates are optimal. So that is for each dimension n, there is an n-dimensional complex torus T such that this automorphism group contains a free abelian group of maximal dynamical rank n-1, okay, which is of positive entropy, if this n is greater than or equal to 2. Okay, so after this structural theorem, it is natural to ask whether one can classify the n-dimensional Compact-Kähler manifolds or projective varieties admitting a free abelian group of automorphisms of maximal rank n-1. Okay, so this is proposed by Ding and Sibony, as well as in Ding, Hu, Zhang in 2015. Or more generally, one can ask if just given a rank R, whether we can classify these varieties admitting a free abelian group of automorphisms of rank R. Okay. But even the maximal rank R equal to n-1 is still not fully solved. The content well studied this question in 1999. Indeed, in dimension 2, such X is either a complex torus, an Eric surface, a K3 surface, or a non-minimal rational surface. Okay, so in dimension 2, this question has already been well understood by content. And in higher dimensional case, when X is projective and n is greater than or equal to 3, Zhang proved in 2016 that either X is rationally connected or X is birational to a quotient of a complex torus, so-called the Q abelian variety. But still, when X is rationally connected for the dimension greater than or equal to 3, it is still unknown whether there exists such an example which is not birational to a quotient of a complex torus. So in our paper, we study this question from the arithmetic viewpoint. So in the following, we shall always assume that X is a smooth projective variety over the field of algebraic numbers. So we recall the Weyl height theory. So it asserts that there exists a unique homomorphism from the Picard group to the functions on the rational points up to a bounded function. So this means for every line bundle D, we can assign D a function on the rational points. Okay, so this is compatible with the embedding, the addition, and the pullback of divisors up to a bounded function. And roughly speaking, those functions measure the arithmetic complexity of rational points. For example, if we consider a very ample divisor H, and then it defines the embedding, then in this case, this Weyl's height function is the pullback of the absolute logarithm height in the usual projective space. Okay. So this is the classical Weyl's height machine. And on the other hand, Core and Silverman established a canonical height function associated with a single endomorphism. So that is, if we consider an anamorphism, surjective anamorphism on X, and where D is an R divisor, which is an eigenvector of the pullback operation. Okay, this is a linear operation. So that the associated eigenvalue is greater than 1. Then there is a unique function. We use this HDF hat, okay, satisfying the following. So first, the difference between this new function with the previous classical Wales height function. So the difference is a bounded function. So this means that this function associated with this anamorphism is really a height function. And secondly, it is compatible with the anamorphism. So that is, if we compose it with the anamorphism F, then it simply means that we can put this eigenvalue as a coefficient. So this is equal to alpha times the previous height function, HDF hat. Okay, so this is associated with this anamorphism. So that we call this the canonical height associated with an anamorphism F. So it satisfies this factorial property. Okay, so our work is to extend this this single anamorphism to a group of maximal dynamical rank. So we consider a smooth projective variety N over the field of algebraic numbers, and we, as before, we consider a free abelian group G of maximal dynamical rank. That is, every non-trivial element of G is of positive entropy. Then we construct a function. We use Hg hat, okay, on the rational points, such that it is a Weyl height function corresponding to a nef and big divisor on X. So if we say this nef and big divisor D, then this means the difference between this Hg hat and this Weyl's hat Hd is a bounded function. And also, we can find a Zariski closed proper subset Z, which is G invariant, such that away from this bad locus Z, this canonical height Hg hat satisfies the Northcote property. So this Northcote property means so this means the set of rational points with bounded degree and bounded height should be finite. And also, this Hg hat is canonical with respect to any element of G. So that is, it satisfies the second item like this, this equality. So if we compose it with any element G, then this is just it is up to a multiple of the original Hg hat. So actually, this Hg hat is the sum of those canonical heights. We put them together to obtain this Hg hat. And finally, for any point X away from the Zariski closed subset Z, we have this Hg hat vanishing if and only if this X is G periodic for any element G. Okay. So this theorem extends Silverman and Kawaguchi's nice works from surfaces to high-dimensional varieties. And as applications, we also talk about the Kawaguchi-Silverman conjecture as the consequence of this theorem in our situation. Okay. And also some other arithmetic applications like the potential density and the bounded height property are also discussed in our paper. Okay, I will stop here and thank you for your listening.